Hi, welcome to this presentation where I present this research titled Dueling Network Architecture for Deep Learning Reinforcement. For this presentation, I would like to start with an introduction of some ideas. We'll go to the background and motivation for this research paper. I'll give you a brief overview of the methodology used in this paper. Then we'll talk about the experimental results that we received from this paper. Then I would like to end with a summary of the research as well as provide some of my own opinions on this paper. Starting with the introduction, deep learning reinforcement is this machine learning methodology where we have an environment and we have an agent. The agent interacts with the environment and achieves some goal. The environment has states S for each time t, and the agent has a set of actions that it can take in said environment. When the agent takes an action A in state S inside the environment then rewards the agent with some reward value, and the agent then uses that reward value to kind of achieve its goal by optimizing the policy function. The policy function is essentially what the agent is approximating to kind of learn its goal. And talking about the policy function has many different aspects to it. Q value is one of the values that leads to a good policy function. And what is Q value? Q value is basically quantifying the quality of a given action in a state. Say if we're in state S, the agent takes an action A. When the action A is taken and then we follow the optimal policy, how much expected reward can we expect given that we took that action in said state? So essentially, it's an expected reward given we take an action in a state and follow the optimal policy. And essentially, Q value is very computationally heavy to calculate. So we have these things called Q networks. They're basically neural networks that approximate the Q value for a given state and action. And so essentially, in this current state in 2016, when the paper was released, there was one way of estimating a Q network, and that was through a single stream of the Q network. And the expected outcome was the Q value from this Q network that will then be used to approximate the policy function. Let's talk about the background and motivation for our research. The Q networks in 2016, even the state of the art, had slow convergence. It had action sensitivity. And let me talk a little bit about this. So essentially, the slow convergence stems from this fact that you're evaluating each action in every state that is there, and we do that every time the agent is interacting with the environment, and that's why we have slow convergence. And then action sensitivity, and this idea was proposed in the research. Imagine the Atari game where you have a car and you move the car, and you either shift the car left or right. So those are your two actions that the agent takes in order to avoid a collision. And essentially the reward is given in the state every time it's traveling. When the car collides with another car or traffic, it's given or the game ends, which is a negative reward or end of the environment. So essentially, the idea was that if we have this car that's constantly traveling through multiple states, but no other car is there, so evaluating the actions left and right kind of become redundant because they're not achieving anything, because it doesn't really have anything to interact with. So either going left or right would not really lead to anything, but the reward is still being given to us regardless. And that's what leads to action sensitivity. And so the motivation for the research then came that if we separate the state value and the advantage functions by itself, we can kind of remove that redundancy of evaluating the actions when there's no need to evaluate the actions. And the goal was it can lead, theoretically, it should lead to faster convergence and better approximation because you're removing the action sensitivity. So you're not really evaluating on actions that, regardless of what action you take, it should not have any effect on the environment or the reward. And the faster convergence because you're removing the evaluation of actions in redundant states. It kind of converges faster because you have less computational things to do. So the methodology. So the Q function is this function where we have the expected reward for a given state and action, and you do this for every action in the state, and a higher Q value leads to a better or optimal policy function. And so in this state, in the current state in 2016, we have this single stream model that approximates the Q value by evaluating the reward for a given state and action. And that's how you get your Q value. However, computationally, if we look at the two major components in Q value, the reward, so going back to our first, that we have an environment and the agent, the state value can be looked at as one component, and the advantage, the action by itself, can be looked at as another component. So we're breaking down the reward into these two major components that the reward has, which comes from the state and the action, and we evaluate the state as a state value and the action from the advantage function. And so the arbitrary equation for this becomes that we can approximate the Q value by adding the state value and the advantage. And essentially, this is what it breaks down to. So essentially, we have our state value over here. We don't really need to do anything with it. However, with our action advantages, we kind of need to make sure that we don't have action sensitivity. And we do that by, firstly, not evaluating the actions. So essentially, because it's split into two streams, we can kind of not use the, we can reduce the redundant computations, as well as we have this part of the function, which is the summation for action, for every action in the state, and we divide it, we subtract it from the action, the advantage action that we take, and this kind of acts as the normalization function, similar to how we have in the softmax. We kind of normalize it. So this is our normalizing factor for our action values. And I'll explain what this means in just 1 second. So essentially, we have enhanced stability. And we have this enhanced stability because we're removing this action sensitivity by not evaluating the actions that have no effect, regardless of in the states where either action has no effect on what the reward is. We have improved efficiency by removing these actions. We don't really need to do any evaluation for these actions. And then the reduction of noise. This refers to the reduction of noise in the advantage function, and we do this by using this normalization factor in our equation. And essentially, let's talk about, now that we have this architecture, how are the results compared to the state of the art at that point, which was the standard DQN. And so the environment chosen was the Atari Arcade Learning Environment, which contains of 57 games. And essentially, in this environment, the 57 games have different goals. And so the idea was, if we have the architecture that evaluates Q values, that leads to better policies. If either of the baseline selection, which is made of 50 neurons, which then goes into a single stream, as we can see over here, to evaluate the Q value, which then leads to the optimal policy function. And then we have the architecture of the dueling network, which is a 50 neuron multi-layer perceptron, but then it splits into 25 neurons for the state value and then 25 neurons for the action value. advantage action. And the results from the tests were amazing. At 83% of the time, 43 out of 57 games, the dueling network architecture was able to outperform the standard DQN estimations to provide the optimal policy function. So, on average, the dueling network architecture was able to provide better estimations for the Q value, as well as have so this was done because it had faster convergence, and it was also faster because it has less computations to do. And so, going towards the summary of this paper, the research provided us with this architecture that provides us with an efficient, computationally efficient architecture, as well as stable learning for the Q values that helps approximate the policy function. And the impact that this paper had was we had improved performance in reinforcement learning environments where we had high dimensional and complex environments. My personal limitations for this paper was that the architecture is overly dependent on the state value function. And so the future work direction for this could go into breaking down that state value function into its basic components and then using those to create an architecture for the state value function. And that's all I had for this paper. Thank you so much for listening to me, and I hope you have a great day.